Hi everybody, this is Solideo Gloria Molecular Thermodynamics. We are going to talk about the chapter 1 of Donald McQuarrie and John Simon's book, Molecular Thermodynamics. So chapter 1 is energy levels of atoms and molecules, and I'm going to cover chapter 1 with four lectures or four modules. Okay, so first one is the quantum mechanics to thermodynamics. We begin. I assume that you have learned thermodynamics in your undergraduate, first entry level of physical chemistry, then quantum mechanics. Then we combine them together, and we go back reverse way, quantum mechanics to thermodynamics. That's what we do in this lecture, molecular thermodynamics. Okay, so this is overview of what we are going to do in this semester, in this lecture, in the grand picture. So what we have here is we begin with quantum mechanics. Basically, thermodynamics is a description of state and property of a state. So, and then the relationship of state functions, change of state, like that. Those are topics of thermodynamics. Thermodynamics here. And then this is just a macroscopic view. We deal with matter. We don't consider any detail of it. So this is macroscopic view. On the other hand, there is a microscopic view. The microscopic view deals with atoms and molecules. Then we should apply not classical but quantum mechanics to calculate or to appreciate the quantities involved by molecules and atoms. So that is quantum mechanics. So we covered both. We did this thermodynamics in completely macroscopic viewpoint. And then we dealt with atoms and molecules in quantum mechanics in completely microscopic viewpoint. And then we will combine these two by statistical mechanics. Okay, that's what we do. When you study Robert Silvey's physical chemistry, that's what we do in our undergraduate courses, and then this is the chapter 1 through 8 thermodynamics, chapter 9 through 15 quantum mechanics, and then there is a little chapter 16, which is statistical mechanics. The beauty of it is that it doesn't go really much detail, but very effectively place a bridge from thermodynamics to maybe quantum mechanics to thermodynamics. Yeah. What we do in this molecular thermodynamics, what we do is that we begin here, quantum mechanics. In quantum mechanics, in this first lecture, I will just briefly describe how we do like quantum mechanical approach to a problem. Basically, we solve Schrdinger equation for a given matter, given problem. That is a Hamiltonian wave function, energy wave function, h psi equal E psi. That's maybe ABC of quantum mechanics. So we solve Schrdinger equation, and then we obtain energy levels, which is quantized. And that is, each level is in other words, it's a state. So molecular state energy, that's what we obtain from quantum mechanical calculation. What those are is, in reality, is energy levels. Energy of the level. What level? Electronic, vibrational, rotational, translational. I just ordered it in size, bigger to small. So electronic energy, vibrational energy, rotational energy, those are obtained by solving Schrdinger equation. So we are going to briefly describe how we do in the next couple of slides. And then once we obtain the energy levels, energies of each molecular state, then we can calculate this, well actually that's not it, but e to the ei over kT, okay? This K is the Boltzmann factor and T is the absolute temperature. So sum of this, okay, sum of this to the level or state, that we call partition function. That is partition function. We obtain partition function, actually sum of state. State sum is a partition function. And then from the partition function, statistical mechanics clearly showed up how it does. Like this, given the partition function log Q, natural log Q, times minus KT will give you A is Helmholtz free energy, which is thermodynamic state function. Given the state function in its natural variables, you can obtain all other state functions. That's what we learned from thermodynamics. That's how we do. So we basically calculate molecular energy levels, rotational, vibrational, electronic, and translational molecular energies, and then we summed up. Well, how do we sum? Well, which is the last slide of this lecture module. How it does is that each molecule has this. Each molecule has rotational, vibrational, electronic, translational energies. And then we summed up each molecular energy to bulk energy. If there is a 1 mole of molecules, then you have collect those Avogadro's number of energies. And then minus e to the minus that energy over kT. But exponential sum of exponentials. No. So exponential of sums is actually sum of exponentials product of exponentials, like that. Yeah. So this is basically what we decomposed partition function into a molecular partition function. So bulk matter partition function is a product of molecular partition function, and molecular partition function is also product of each individual energy partition function. That's how it does. And then we can get the total partition function, a whole partition function, and then we'll get the bulk matter macroscopic state function. This is the general grand scheme of what we do. Okay, so this is just an elementary idea of quantum mechanical approach. So before we do that, we want to find out or understand it from classical mechanics to quantum mechanics. Classical mechanics, we describe the system by observables or dynamical variables, which are momentum and coordinate, which means that all kind of physical quantities can be described by this momentum and position coordinate. In terms of Cartesian space, x, y, and z, and px, py, pz. In this case, these are position and momentum, 3 components in 3 dimensions. Or in general, p, q, qp, yes, that's how it does. And then f is described by this p and q, and then acceleration is described by p and q. So this is the equation of motion, or Newton's equation of motion, whatever, however it describes it, F equal ma. How it does is that force is negative gradient potential, which is negative gradient potential, and maybe I'll just write like that, and then which is then multiplied by double derivative of r let me just do it over here. Negative gradient potential equals, that's force. Basically, this is force. And then mass multiplied by acceleration, which is like this. Okay, so this is basically what this is. This is what this is. And these are the dynamical variable. In this dynamical variable, we call those observable. Okay, so observables are, or dynamical variables are x and y and z, the position coordinate, and then px, py, pg, that's a momentum coordinate. This is how we describe motion in classical mechanics, or state in classical mechanics. So given this position and momentum coordinate at a given time, and given with the equations of motion, we can determine state at any time, any given time, whatever, past, present, or future. That's how classical mechanics operate. On the other hand, in quantum mechanics, we don't do that definistic trajectory in such a way that instead we describe state by a given coordinate at a given time in such a way that P and Q and some time t with the equations of motion, we describe or denote the state with a state function. That is wave function. Like this, psi of xyz as a function of coordinate and time. In this case, we are dealing with time-independent case, time-independent wave function. That is a solution of this equation. This equation is a Schrdinger equation, which is derived by wave equation. Yeah, wave equation is equivalent to this one. If I say wave equation, round scale u, round x in one dimension, something like round scale u, round t square like this. And here there is a kind of a constant term here. So anyhow, this is the equivalent in quantum mechanics of classical Newton's equations of motion. So the psi is a wave function. So this is the differential equation for the wave function. That is we call Schrdinger equation. This Schrdinger equation, if you look at, this is 1D Schrdinger equation in x dimension only. So minus h bar square over h bar is what? H over 2 pi, 2m, mass of the particle, and then the d square, because there is only one variable, psi dx square plus potential as a function of coordinate only, position only, and psi x equal E psi x. So this part, okay, which is minus h bar square over 2m and d square dx square plus v over x, we call this Hamiltonian operator. So I just mentioned that in the previous slide as h psi e psi, yeah, just like that. So this is a linear operator, and that represents the observable. Actually, I'm not going to dive into much detail here. So positions xyz the same, but each momentum operator is replaced by this differential operator. So px is minus I h bar round x. Py is minus I h bar round y, like that. Okay, so this is basically mapping of classical mechanics to quantum mechanics. By doing so, what we get is energy and wave function of the molecules and atoms. So then what we need is that what is this potential energy of the molecule? What is the potential energy, how it is expressed in terms of the coordinate in of the molecular assembly, just like that. Okay, so how it does work, how it operate. So given the potential in terms of coordinate. So if there's one dimension just like this, there must be an expression for potential energy. And then we covered mostly in our elementary quantum chemistry, particle in a box problem, and rigid rotor problem, and harmonic oscillator problem, hydrogen atom problem. Well, these are 1925 Schrödinger's paper in Germany. So I teach you something, yeah. So anyhow, he solved this analytically. Well, he solved all analytically solvable quantum mechanical problem. Then that's done. So no more analytical solutions are possible or found. So that's what his kind of his work. So particle in a box, V is equal to 0 or otherwise infinity. That's the simple. Rigid rotor, which is 0, much simpler. Harmonic oscillator, which is 1/2 kx squared. A hydrogen atom, the Coulomb energy between proton and an electron. That's what it is. So given potential as a function of coordinate, then we can solve this because this is the kinetic part and potential part. The total energy Hamiltonian is given, and then we solve that. We obtain psi, and from psi we can obtain all dynamical variable, given that that dynamical variable is expressed by a operator. In this case, this A operator gives you A, which is the eigenvalue, or if that's not the case, then we obtain an expectation value, which means that average. Anyhow, we can get energy. So given the potential, we solve the Schrödinger equation, obtain the wave function, which is the state function, and then energy. So given the energy, what do we get? We do, this is the molecular energy, and then we summed up, get partition function, and then we obtain thermodynamic state functions. So that's how it works. I just briefly describe how it works. So how it works in such a way that there are statistics like Fermi-Dirac or Bose-Einstein, much detail in microscopic view, but in general, if there are lots of many available state, then we can use a simplified version of it, which is Boltzmann distribution. There are n molecule, and then there are, each molecule has energy, which is E epsilon. In this case, this epsilon first, epsilon second, epsilon n. Okay, so there are n molecule, there are n epsilons. Each epsilons is a translational plus rotational plus vibrational plus electronic, just like that. Electronic. So these are all obtained from particle in a box, rotational, rigid rotor, harmonic oscillator, something like in case of hydrogen atom, we do have analytical solution. In case of molecules, we can obtain that by solving Hartree-Fock equation using computer software. Anyhow, we can obtain the energy of molecule. So electronic energy. So each molecule has translational, rotational, vibrational, electronic. So this is a decomposition. Each epsilon is decomposed this way. This is the maybe this is a molecular summation, but this Q, which is actually Q, the small q, I'm sorry, small q is e to the minus of kt. Then e to the minus sum of kt. Then this one is each term, the product of each term, like q trans, q root, q vibe, q electronic, ELEC, yeah, just like that. So we obtain molecular translational, molecular rotational, molecular vibrational, molecular electronic partition function. And then what? If there are n molecules, we exponentiate with n, that large number. Okay, this is how it works. And then we obtain, this is what? Q. Then what we do is that A is given minus KT and then Q. Then we obtain thermodynamic quantity, thermodynamic state function with the given molecular energies. And then this is how it works from quantum mechanics through statistical mechanics and then finally thermodynamics. So this is first lecture that outlined and show you overview of how we do in molecular thermodynamics lecture. Thanks for listening.